I hope it's okay with everyone. Otherwise, switch off your camera, mic, or whatever. Okay, good. So it started on YouTube, and now I will share my screen and probably start. All right. Let me first of all say that I already talked on this topic at the live seminar at Weizmann in the beginning of the pandemic. But I think the intersection of the audience is only one person, so it's not a big problem. And also the talk will be slightly different. I will emphasize different parts. Okay, so is my screen visible, the screen I'm sharing? Very good. The talk is about wavefront sets of distinguished representations. It is a joint work with Eitan Sayag, and it appears on the archive in 2 preprints. The work was inspired by previous works of Haris Weig, Prasad, and Prasad Sakilaridis. So let me start. So we fix a local field F and a reductive group over it, and an algebraic subgroup H of G. And we denote by boldface the algebraic groups, and by usual Roman letters their F points. We consider also the Lie algebras of G and H, and denote by G0 and H0 the Lie algebras of the F points. And we denote by script n of G star the nilpotent cone in the dual space to the Lie algebra of G. That's just some piece of notation. Now, an irreducible representation of, should be of G. So an irreducible representation of G is H-distinguished if it has an H-invariant continuous function. So we consider irreducible admissible representations. In the Archimedean case, also smooth Frechet of moderate growth. And we denote by ir G with subindex H all smooth admissible H-distinguished irreducible representations of G. Now, to every such representation, one can attach a collection of nilpotent orbits. This collection is called wavefront set, and I'm interested in top orbits in this collection. So it's some collection of nilpotent orbits in the F points of the dual Lie algebra. I will not give you a definition because actually the theorems we prove are not about this collection, but about other collections that uniquely determine this collection. If we will ever get to the proofs, then I will also give formal definitions. So far, it's just some invariant of representation, collection of finitely many orbits. And the philosophy of constant Kirillov orbit method is that the representation should be viewed as some quantization of these orbits. Now it's a very big question of what irreducible representations are distinguished. And there is no general answer. There are some answers in some particular cases. For example, the previous talk we had on this seminar answered this question for restrictions from GLN+1 to GLN for representations of Arthur type. And already this specific case is extremely important, but unfortunately no general technique. It's a very difficult question. And in this talk, we are saying something about distinguished representations in terms of these invariants. So we are giving a necessary condition, which is far from being sufficient, but it's some simple condition that holds for all cases. Namely, let me first give you a conjecture that we prove partially. that for any reducible distinguished representation, the restriction of top orbits of one of the top orbits in the wavefront set to H0 includes 0. So that's reasonable because the condition of distinction, in other words, means that the restriction of pi to H includes the trivial representation as a quotient. So the restriction of the orbit to H should include the trivial orbit, which is the 0. So that's the reason for the wish, and here is some theorem in this direction. A theorem is only for f of characteristic 0, and it's different in different cases. When f is Archimedean and the subgroup is spherical, then we prove the following. It's almost this. We restrict not just the wavefront set, but its stable orbit. So to each orbit over the field F, there corresponds an orbit over the algebraic closure, and the restriction of this orbit over the algebraic closure to H includes 0. If F is p-adic, we prove a different condition. So even this condition can be rephrased as saying that the wavefront, I will just say wavefront, I will not say this O. So the wavefront intersects the orthogonal complement to H0, orthogonal complement in the dual space G star, which can be identified with the dual space to G mod H, G0 mod H0. So here we prove that it includes the bold G acting upon, is included in the bold G acting upon orthogonal complement. And here we say that it lies in the closure of G acting upon the orthogonal complement. So the whole wavefront lies, not just one of the orbits here, but not in G H0 perp, but rather in the closure of G H0 perp. And that's a much weaker condition. I don't think there is a true reason for a difference between Archimedean and non-Archimedean cases. I think that both statements holds for both cases, and in fact, this conjecture holds for both cases. But this is an attribute of our proof. In our proof, in the Archimedean case, we use Lie algebras, which are not applicable in the proof of the p-adic case, and vice versa, p-adic proof uses some p-adic results. So let me just tell you what does it mean spherical, the condition on sphericity here. It means that the bold H has an open orbit on the flag variety of bold G. Well, flag variety is a quotient by the Borel. Borel is a maximal solvable subgroup, or in other words, minimal parabolic subgroup. Parabolic means that this flag variety, this quotient, is complete. So H being spherical, it's a very important condition. In particular, this includes symmetric pairs. Symmetric is fixed points of involution. So it's at some point, many problems from representation theory were generalized to relative representation theory, namely equation on H-distinguished representations for symmetric pairs. And then in the past decade, most of them were generalized to spherical realm, and we also work in the spherical realm. This is without this condition, it's hard to say something actually. One more general, still reasonable condition is for H to be F spherical, which has to do with a quotient by minimal parabolic subgroup. So I think here the true condition is F spherical, should be, but we managed to prove for spherical. Also, maybe the condition is not needed, so I didn't put a condition in the conjecture. Why? Because the smaller the H, so too small H will not be spherical, but the smaller the H, the bigger the orthogonal complement. So it becomes easier to intersect the orthogonal complement. So it might well be that you always intersect the orthogonal complement. Just if H is too small, then it's not interesting to intersect its complement. But some evidence is that in the p-adic case, we do. We don't need the Archimedean condition. We don't need the sphericity condition, sorry, but we don't need it in the Archimedean case. All right, so any questions about the setting, the conjecture, or the theorem? Please, it's a good point to ask. Okay. So if not, I continue. So here is some general corollary for all fields of characteristic zero, namely the Archimedean or periodic. Suppose that H is a unimodular spherical subgroup, then we may ask, let us look on all H-distinguished reducible representations of G and check for each what is the dimension of the wavefront set. This is the same as twice the Gelfand-Kirillov dimension. So what's the maximum Gelfand-Kirillov dimension? We get that it's the dimension of, in some sense, the nilpotent cone of the pair, namely the intersection of the nilpotent cone of G0 star with G acting upon the orthogonal complement to H. So in other words, it's the dimension of the maximal among the orbits who intersect the orthogonal complement to H. Now there are two applications of this. We may ask two questions on the two extremes. When does pi have a generic representation? So having a generic representation is equivalent to H being minimal. So the existence of a generic H-distinguished representation is equivalent to H being minimal, namely of dimension equal to the dimension of the flag variety up to center. So the center of G plays no role here. If we assume there is no center or just quotient H by the center, then it will be of dimension equal to the dimension of the flag variety. On the other extreme, if there are no infinite dimensional H-distinguished representations, then H is maximal. What is maximal? Maximal, it means it includes the split semi-simple part of G. In other words, the quotient is compact modular center. Or equivalently, we can say that there exists an infinite dimensional H-distinguished representation. If I don't leave, there exists an unipotent element of G without H. So this minus is just Z minus. It's the complement of to H in G. So this is a uniform application that we can say when there exist generic representations, that's when H is minimal, and when there exists infinite dimensional H-distinguished representation, that's when H is not maximal. Right? So from now on, I will assume that F is Archimedean, or for simplicity, F is R. So assume F is R. Then one can simplify the formulation due to the following theorem by Rossmann, which uses another theorem by Boro-Brzezinski and Anthony Joseph. For any irreducible representation, there exists actually a unique stable orbit in this wavefront 0 of pi. So unique orbit over G bolt with algebraic closure. And then we will just denote this orbit by O of pi instead of this notation. So we will be talking about the orbit of pi, and it will be a complex orbit. So let me give you first applications to symmetric subgroups. So to every symmetric subgroup, there corresponds a real form of bolt G, a different real form. There is our usual G is a real form of bolt G, and to any symmetric subgroup of bolt G, there corresponds another real form. And actually, this was the first motivation to study symmetric subgroups. One actually wanted to study real reductive groups and did this using symmetric subgroups. But one can also use this in the other direction. We have a symmetric subgroup, define a real reductive group. But there is a constant Sekiguchi bijection between H orbits on the orthogonal complement to H, which can be identified with G mod H dual, or also can be identified with the -1 eigenspace of the involution that defines H, sometimes denoted P. So between such orbits and the real orbits, and when I say orbits in this talk, I mean nilpotent orbits, and the real nilpotent orbits on, it should be G0 star because it's real. So one difficulty of relative representation theory of the study of distinguished representations is that there's no category. So we have irreducible objects, H-distinguished representations, but they are not simple objects of any category. So Prasad suggests to study these objects by studying just representations of a reductive group of GHR, the real form of both G corresponding to G mod H. So that's just a philosophy that this group somehow is responsible for H-distinguished representations of G. So that's the idea that I learned from Dipendra Prasad. But in particular, Dipendra showed in the PID case, and our theorem from the previous slide extends this also to the real case, that there exists a generic representation if and only if this GRH is quasi-split. And also, again, follows from the previous slide that there exists an infinite dimensional H-distinguished irreducible representation if and only if this GRH is not anisotropic, is not compact modular centric. But in general, our corollary says that if pi is H-distinguished, then its orbit includes a real GRH orbit. So, for example, it's known due to Vaughan, I think, or Rossmann. Actually, it follows from this theorem of Rossmann that the orbit of pi includes a real orbit because this wavefront 0 consists of real orbits, real orbit for G. But our corollary says that if in addition it's H-distinguished, then it includes a real orbit for the other real form. It also enables so it's a very nice formulation of the theorem in this case because real orbits are classified by Okhta and Djokovic. So our conditions that the orbit intersects H orthogonal complement, there are just lists of all orbits who do this. So our answer is very explicit in this case. But there is a further conjecture due to Prasad following the same philosophy that if G and H are split, then the existence of a tempered H-distinguished representation is equivalent to the existence of a generic H-distinguished representation. So the condition on splitness of G and H, it may be possible to relax it. So this corollary, together with results of Harris, because he bounded what can the wavefronts of distinguished representations be, together they apply this conjecture for most pairs, GH. Okay, any questions, or shall I pass to spherical pairs?
Dima, what is GRH? Is it the real form for which the maximal compact is a real form of H?
Yes.
Okay, thank you.
All right. So one family of spherical pairs is diagonal pairs. So we assume H to be reductive, and we consider the group G times H, and assume that delta H in it is spherical. So H embeds both to G and to itself, we take diagonal. If this is the case, then we can ask for a more general question. We can take a reducible representation of G restricted to H and ask not just for home and to trivial representation, but for home to any irreducible representation of H. So our theorem translated to the bigger pair delta H and G times H says that in this case, the orbit of pi restricted to the Lie algebra of H includes the orbit of tau. So again, it's very natural. If restriction of pi includes tau, then the restriction of the orbit of pi should include the orbit of tau. It's very natural, but it gives a simple necessary condition on distinction, which otherwise is very difficult. This condition, we claim nothing about its sufficiency, but it enables you to discard a lot of representations. So we can make it explicit for classical groups. So for classical groups, the nilpotent orbits are described by a Jordan form of the matrix. So Jordan form gives you a partition of N. I will denote this partition by lambda of pi. And this condition can be explicated in terms of partitions in the following way. So suppose G is a classical group, which is a GL or orthogonal group or unitary group. And H is a group of the same type, but of size 1 less. Embedded in the top left corner of G, let us take irreducible representations, pi of G and tau of H that talk to each other. Then we look at the partitions and we consider transposed partition for both of them. And then for any index I, the absolute value of the difference of the two transposed partition is at most 1. So it may happen that one of them is shorter than the other, then we prolong the other by just writing zeros in the transposed partition. There are partitions of different numbers. This is of n plus 1 and this is of n, but it's no problem for this formula. And this is related to Gann-Gross-Prasad conjectures for non-temperate representations. So they have a similar condition, except that they consider both less and more. So less in the sense that they restrict the type of representations. They only talk about representations of Arthur type, but more because they look on Arthur parameters. Arthur parameters have discrete part and continuous part. The discrete part is, in terms of, at least for GLN, the discrete part is exactly this transposed partition. But we say nothing about the continuous part. So for the discrete part, our condition is very similar, except that Gann-Gross-Prasad demand more. This less or equal to 1, it can in particular be 0. They can coincide for some. Gann-Gross-Prasad, and it was shown to be true by K. Chan, that if you get 0, then also if the two parts are equal for some I, then they're also equal to 1. So if lambda, but that's not the case in general. It's only the case for representations of Arthur type. Otherwise, one can give a counterexample when the discrete parameters, the partitions, are the transposed partitions are the same for some index, the same but not 1. Not far to type. So we say about a more general class of representations, but we say much less. So further applications are to Jacquet quotients. We can take an irreducible representation of G and take the Jacquet restriction to Levy subgroup. So we take a parabolic, P equal LU. We take Jacquet module. Jacquet module is an admissible representation of the Levy, which might be reducible. Take an irreducible quotient tau. Then we say that the orbit of pi lies in the, the orbit of tau lies in the orbit of pi restricted to P star. So let me explain. Canonically, the Levy is not a sum, but rather is a quotient of the parabolic. It's P mod U. The algebra of the Levy is P mod U. So the orbit of tau lies in L star by definition. But since L is P mod U, L star is a subspace of P star. It's the orthogonal complement to U in P star. The orbit of pi lies in G star, and the restriction is an onto map from G star to P star. So O of pi lies in G star, projects to P star, and this projection should include O of tau. That's what our corollary says. Let me show you a picture for GLN. Let me first show you a proof. How does it follow? So the proof is that we consider the parabolic subgroup, which is in some sense diagonal. Namely, the first coordinate should lie in P, and the second coordinate should be projection of the first coordinate to L. Well, that's a spherical subgroup of G times L. And then the tau being a quotient of pi means that there is a home from pi restricted to P into tau, where tau is extended trivially to U, which in turn means that there is a home over H from pi tensor tau twiddle to C. So a functional on pi tensor tau twiddle, and the tensor should be completed. And then we use our theorem. So now, what does it mean for GLN? For GLN, it means that if A00B lies in O of tau, then AC0B lies in O of pi for some C. And this gives a non-trivial question in linear algebra. When does it happen? If you know a partition, the partition of A and the partition of B, what are all the possible partitions of AC0B? So it's easy to see that AC0B is always nilpotent. So what can its Jordan form be, given the Jordan forms of A and B? Each pair of Jordan partitions gives you many possibilities for this. But what are all the possibilities? The minimal is, of course, their concatenation. Just put C equals 0. The maximal is generic C. It's what's called induced orbit, and for GLN, easily described by adding the partitions. But what are all the possibilities? It's not any possibility between them. So any other possibilities between them, it includes this in the closure and lies in the closure of this one. But not everything in between is possible. And my postdoc, Zhu Zhang, is working on this. And the answer seems to be that it's possible if and only if the corresponding Littlewood-Richardson coefficient doesn't vanish. And the proof is not by linear algebra. The proof is by some geometric representation theory, geometric satake, some very interesting proof using some, so it's probably a question in geometry, not in linear algebra. And one can ask the same questions for other groups, and that is probably even more difficult. So there is also something interesting philosophical here, which maybe there. I'm pretty sure there is some deep mathematics below this. What is Littlewood-Richardson coefficient? I mean, it's used in representation theory. It says it's talking about finite dimensional representations of GLNs, the algebraic ones. This non-vanishing means that the algebraic representation of GLN plus K given by mu restricted to the Levy includes the exterior product of the representations given by lambda of A and lambda of B. So here we are talking exactly about this, except that we are taking the Jacquet restrictions of infinite dimensional representations. But somehow one problem talks to the other, maybe through Langland's correspondence. I don't know. So I will be glad to hear suggestions. Right, so these are the applications to Jacquet restriction. So any questions up to now? So if not, I will show you a twisted version of the theorem. So first of all, let me say that I'm talking about H-distinguished representations, but also we can allow H to act by a character or by any finite dimensional representation, and it's the same. It's the result in the paper is actually about finite dimensional representations of H. But if H is not reductive, it has unipotent part, and on this unipotent part we put a character, we can also say more. So we have a twisted version of the theorem. More precisely, we have twisted induction of spherical pairs. So suppose we have a parabolic with Levy decomposition P equals LU, and we have a spherical subgroup of the Levy. Then there is no notion of a spherical induction, namely we just form H to be SU. It is also spherical. But suppose that we also have an algebraic character of U that extends to H. Then define a character of H by exponentiating this psi. So we have an algebraic character psi from U to R. We consider exponent of I psi of U, a unitary character of H. And this a priori it's unitary character of U, but we assume that it extends to H and we don't care how it extends. What is it on S? We just give it to extend, of the sky. Consider also deep psi. Deep psi is the differential of this map. It lies in U star, but U star lies in H star, because H is SU. And denote by H chi those irreducible representations of G whose restriction to H has a home into chi, non-zero home into chi. So the theorem is that for such representations, the orbit of pi restricted to H includes deep psi. So it also includes zero, but more importantly, it includes deep psi. So one application is for Shalaika models. We can give a necessary condition for the existence of Shalaika models. So take G to be GL2M. Take the Ziegel parabolic. So the L will be GLN times GLN. And inside it, there is the easiest spherical subgroup in the world, actually symmetric subgroup, S, just diagonal GLN. The U nil radical of the parabolic is matrices n by n. So the H has this form, GA0G. And the theorem is most powerful when you take a generic character of U, take psi to be generic character. If it's possible, S has to fix it. But S exactly, in this case, S is exactly the stabilizer of this generic character. So generic character is taking trace. To fix the trace, we need to put G here and the same G here. And such models are called Shalaika models. So if pi lies in H chi of G, one says that pi has a Shalaika model. So the corollary of this theorem is that lambda of pi consists of even parts only. Partition consists of even parts. Equivalently, the transposed partition has even multiplicities. Let me show you one more model of this kind. It is the Klitschko model. So in Klitschko model, we take G to be GLN plus K. And as a Levy, we take GLN times a bunch of GL1s. And as S, we take the symplectic subgroup of G here. So we take matrices of the form GA0B, where B is upper unitriangular. So it has zeros below the diagonal, ones on the diagonal, and whatever above the diagonal. And the character, the non-degenerate character of B is just by summing all the elements just above the diagonal. So these Klitschko models interpolate between symplectic models and Whittaker models. Whittaker is when n equals 0. Symplectic is when k equals 0, just symplectic subgroup, and Klitschko models interpolate between them. And the condition we are getting is that for any irreducible representation of G that has a Klitschko model, the number of indices for which the transposed partition is odd should equal the k, this k of the model. So in particular, for each irreducible representation, there is exactly one k satisfying this condition. And what is nice about this case is that for unitary representations, this condition is also sufficient. So this is the only case of models when our theorem actually gives a necessary and sufficient condition for unitary representations. For non-unitary, that's the only possible k, but sometimes even for this case, there is no model. For unitary, what is nice is that if you take direct sum over all k, you'll get a model for all unitary representations. On the missing side, it has nothing to do with this talk, but just for general knowledge, on the missing side, for all models that I mentioned today, uniqueness is proven. Just for Klitschko models, it's proven only in the non-Archimedean case. But I'm sure it holds. Just not proven yet. For Shalaika models, uniqueness is proven, and for everything else I mentioned today is proven in all cases. Okay, now exactly as with the untwisted theorem, there is a version for strongly spherical pairs. So we take, again, a parabolic inside it S, but strongly spherical, which means that delta S inside S times L is spherical. And then we again take a character of u of the inner radical of this parabolic, and extend it to a character of chi. Hope it's possible. Now we take an irreducible representation of G and an irreducible representation of H. Sorry, of here I mean S. I apologize. So it's a virtual talk, and I have here virtual symbols. This H should be S. So the reductive part of S. But then we produce from it an irreducible representation of H by tensoring with chi. So on the unipotent part, we put a unitary character chi, which is exponentiation of an algebraic character psi. And on the reductive part, we put an irreducible representation. And we put a condition that hom over H from the restriction of pi to H to tau tensor chi is non-zero. Then O of tau plus the differential of psi lies in the restriction of the orbit of pi. So then we restrict the orbit of pi to H. We need the orbit of this tensor. The orbit of this tensor is just the tensor of the orbit of tau. And d psi, because chi comes from psi is additive, so its orbit is not zero, its orbit is itself. So it's differential. So this is a corollary. Now let's apply it. So let's first apply it to Rankin-Zelberg models. We take G to be GLN plus K, where K is at least 1, and L to be GLN plus 1 here, and a bunch of GL1s. And we take S to be GLN. So L has this, but when we embed S, we take G001. And psi, so the unipotent will be just this, because our L includes the zeros and the 1 also, so unipotent is just this. And a generic character of this unipotent is by summing again all the elements above the diagonal, just above the diagonal, so summing the underlined entries. And apparently the condition here is exactly the same condition as for the case when K was exactly 1 and there was no twist. So now there are partitions of very different numbers of n and n plus k, but still the condition is that we take transpose partitions, and for any index I, the difference is at most 1. And so the corresponding models are called Rankin-Zelberg models. We have necessary condition for their existence. Moreover, one can do the same replacing GL by O or by U. And then the models are called Bessel models. So we get analogs for OPQ, UPQ, and also ONC. For GLN, it was also working for GLNC, all the same. And the same condition is obtained on the partitions. Now, actually, the Gann-Gross-Prasad conjecture includes also Rankin-Zelberg models and Bessel models. And again, it's compatible in the same sense that our condition is weaker, but that's okay because we work with more general class of representations. So in terms of orbits, this is the only thing one can say in terms of orbits. And it will be necessary, not sufficient. Okay.
So in the title, though, do you explain what is strongly spherical?
Yes, it means this condition. So if we say that S and L is spherical, strongly spherical, it means first of all S is reductive, and then delta S, the diagonal, is a spherical subgroup of S times L.
So, but you have the term strongly spherical.
Yes.
So what is the meaning of strongly?
Well, S, so S.
Okay,
so
okay, I see. So it
means we put this delta.
Okay.
Put the diagonal.
Yeah, I got you back.
So can I add a word?
Yes.
If you take in H, you have G on the top left, and then you have ones of like GL1 times GL1 across the diagonal, right? If you change that to also GLN, so you have GLN embedded diagonally, but you take two copies. So you have one G like you have, and then you have the rest are like H in GLN and repeated. And you take the character, the same character of psi you took, but with trace instead of the generic character. Then you also have uniqueness. Then it's like a doubling, because you have representations of GLN times GLN, and you have uniqueness, and we base our Rankin-Selberg integrals on this uniqueness. So there's in the appendix, one of the appendices of the work we just uploaded, there's a construction which is just based on this matrix and uniqueness.
Okay, very good. Then it's interesting to see what necessary condition do we get on the partitions. So it's linear algebra. To do this, by the way, to derive this condition from this one, it is a problem in linear algebra that did not require geometric representation theory that I managed to solve with some small help of Joseph Bernstein, but it was not easy. So I gave it to students, to young students, to some master students for a summer project. They did something, but they couldn't solve it. And then I could not solve it in my usual approach, but then I talked to Bernstein, and not only he gave me small advice, but also I suddenly became a student. And then acting as a student, I could solve it. And I still have a couple of open questions in linear algebra here that I think I can solve, but I leave it to the students to solve, or postdocs, or maybe Zhuk will also solve. All right. So any more questions? It's a good point for questions because I said all I really wanted to say, and now I will be saying the things I usually want to say. Okay, so let me go on. So let me describe the proof briefly. So what are the main ingredients? One of them is the following recent theorem of Wehave says that for any nilpotent orbit, if we intersect it with H perp, orthogonal complement to H for a spherical subgroup H, the dimension drops at least by half. Actually, he proves that this intersection is isotropic in all. So there is a natural constant carrier of symplectic formula. He proves it's isotropic. Now, actually, one can conjecture that it's Lagrangian. I don't know counterexamples to it being Lagrangian, but that's not known so far. It's known for symmetric pairs, for example, in some other cases. It's enough for us to know it's isotropic, and actually, it's enough to just know this restriction dimension. Then we actually use not wavefront set. We use a different notion from the theory of Lie algebras. And the theorem is at all, in the Archimedean case, about representations of Lie algebras, not the representations of groups. But in particular, most representations of groups are representations of Lie algebras. So we will define another invariant called the associated variety of the annihilate. It uses a universal enveloping algebra. So let U of G be the universal enveloping algebra. Introduce on it the standard filtration. It's called the Poincaré-Birkhoff-Witt filtration. It is by order of the polynomial, Un of G. We know this Un of G. Then we can consider associated gradient by this filtration, and it will be the symmetric algebra. So since commutator of two Lie algebra elements also lives in the Lie algebra, but by the filtration commutator, it should have degree 2. Instead, it has already degree 1. It means that it lies in lower filter than it should be. So the associated gradient is symmetric, is commutative, and it is a symmetric algebra of G viewed as a vector space, or which is the same, it's polynomials on the dual space of the Lie algebra. Then we define an annihilator variety of any G module in the following way. We first consider its annihilator in the universe enveloping. That's a two-sided ideal. Then consider the symbols of all the elements in this ideal. So for every element of this ideal, there is its symbol. It's an element of the symmetric algebra. Consider the set of all such symbols. So symbol is a nonlinear map, so we're getting a set. Consider G set, take its zero set. It will be a closed subset of G star, Zariski closed. Call this, it's actually called annihilator variety, associated variety of the annihilator. But that's a long phrase. Let me just call it annihilator variety and denote this way, unv of M, it should be, unv of M, G star. So it's very similar to how you define the support of a module in commutative algebra. You take the annihilator, and then you take the zero set. Here, when you have non-commutative algebra, you take the annihilator, then you pass to the commutative algebra through taking symbols, and then you take the zero set. And the theorem of Rossmann is that this zero set, sorry, I'm sorry. This is not due to Rossmann. So it's copy-paste, I apologize. I'm really, really sorry. So this was done by copy-paste. I will even strike through it. So it's due to Anthony Joseph and independently and a different way to Boro Bralinsky, simultaneously, I guess. I see now why I attributed it to Rossmann. Because I write here an irreducible module over G. Sorry, so it's fine to Rossmann, but with some comments. So it uses the theorem of Anthony Joseph that I mentioned. So for any reducible representation of G, but actually the theorem talks about reducible representations of the Lie algebra, and there exists a unique nilpotent orbit over the algebraic closure, such that the annihilator variety is the closure of this orbit. So again, it makes sense. Your model is irreducible, then its annihilator variety is irreducible. Irreducible as a set in Zariski topology. So irreducible modules give us irreducible supports. So that's the theorem, and we will be using it. Now we will also use another variety, which is smaller. It is called associated variety. Here, we don't take annihilators of the module, but we take annihilators of generators. And in non-commutative algebra, this is not the same. So we take a set of generators, doesn't matter which, take its annihilator ideal. It's a one-sided ideal because it just annihilates a subset. And again, take its symbols and take their zero set. Call this associated variety. There is a much better way to define it, but it takes a little bit more time. And they're related. The theorem of Gaber and Joseph says that twice the dimension of the associated variety is at least the dimension of the annihilator variety. So it's an analog of Bernstein inequality for this case. Actually follows from the much more general theorem of Gaber that says that this set is coisotropic in this set. And that's why it is at least of Lagrangian dimension. And then the same theorem also works in D modules generalizing Bernstein's inequality. Anyway, we just need this version, which was proven by Anthony Joseph and generalized by Gaber. So how do we apply those ingredients? The following way. We need a third ingredient. So this is just summary of what I already said. Let me just emphasize that the associated variety is only defined for finitely generated modules because we needed a finite set of generators. For infinite sets of generators, it doesn't work so well. In addition, a simple lemma, well known, I guess, is that if M is generated by an H finite vector, or by a finite set of H finite vectors, then the associated variety, not only it lies in the annihilator variety, but also it lies in H perm. That's because H should lift filtration on the module, instead it keeps it. So it's an easy lemma. And so here is how our theorem reformulated. No, it's actually just repetition of the theorem. But now O of pi is defined in terms of annihilator varieties. So here is a proof. Take this functional, which exists by the definition of H-distinguished reducible representation. Let eta be the non-zero H-invariant continuous functional, and generate a module just by this functional. Generate a module over the universal enveloping algebra. Then this module is non-degenerately paired with pi. Why? Because we have a pairing. The pairing is not zero. It's just by definition of the pairing, it has no kernel in M. And on the other hand, because a function vanishing on O of pi is zero. On the other hand, it has no kernel in pi because pi is irreducible. The kernel would be a sub-representation. So it's non-degenerately paired. And thus, M and pi have the same annihilator. But M is generated by an H-finite vector, eta. So the associated variety of M will lie in the annihilator variety of M intersected with H perp. But intersection with H perp drops dimension of every orbit at least times 2. On the other hand, you cannot drop dimension more than times 2. So the dimension, well, intersecting does not drop. But if it doesn't drop, it means that the top orbit does intersect. Otherwise, if you lose the top orbit, dimension drops. So let me write this again. Twice the dimension of the associated variety of M is at least the dimension of the annihilator variety of M by this inequality, Joseph-Gaber theorem, which in turn equals the dimension of the annihilator variety of pi, because they are non-degenerately paired, have the same annihilator, which equals O of pi, because by this theorem in the previous slide, the annihilator variety of pi is irreducible variety, and it's a closure of its top orbit, which by definition is denoted by O of pi. Then the associated variety here already lies in H perp. So if we intersect with H perp, its dimension stays, but the dimension here drops at least times 2 by this Lie inequality. But from here, it cannot drop more than times 2. So actually, it drops exactly times 2. If it drops exactly times 2, it means the top orbit intersects. So in fact, we proved not only that the top orbit intersects, but also that the intersection includes a Lagrangian and has dimension exactly half the dimension of the original orbit. I don't know if it's an additional geometric condition, or is it true that the intersection is always half the dimension or empty for every spherical pair in every orbit? Okay, any questions on the proof? Okay, yes?
So the Twister version is similar. The proof for the Twister version. So you have the Twister version. Yeah.
The twisted version is similar but slightly different. The problem is that in the usual filtration on the universal enveloping algebra, we lose the character psi. So it's a correction of lower order in the filtration. So we cannot do the same. So we have to change the filtration. But there is such a filtration. There is a filtration that takes care of characters. It's the Kazhdan filtration. And this filtration is used in the theory of W algebras. So we use this filtration, and we define the corresponding annihilator and associated variety. And then the annihilator, we prove that the annihilator variety is the same. And that's because the change between two filtrations is by conjugation action, to which our ideal is invariant, because the annihilator ideal is a two-sided ideal. So it's the same annihilator variety. And since so it's the same annihilator variety. Then we deduce this inequality geometrically from, okay, this equality stays, but we need slightly different intersection. We need intersection with H perp plus deep psi, but we deduce it from this inequality. Then this stays. This inequality stays due to the more general theorem by Gaber, which is good for any kind of filtration, almost any kind. And this lemma, the proof of this lemma is the same. The shaded variety with respect to this other filtration is very different, but we don't care. It's just a tool in the proof. We can use it as a tool. And then the proof has the same logic. So we first wrote a proof using W algebras, but it put additional conditions on the character. It had to be generic and more admissible. But then we derived the proof with no formal use of W algebras, just use of Kazhdan filtration. And the general idea of W algebras that helped us design it. Any other questions, please? I forgot to say the slides are available on my homepage, and they're also available on the seminar on the seminar homepage inside the Google Calendar. And they are also will become available on the seminar homepage. So you can see I have.
It is already available on the seminar homepage.
Thank you, Rami. So they're also already available on the seminar homepage. I have more in the slides. I guess it's. I don't know. Okay, so Rami, you are the boss. Should I continue a little bit or should I finish? I cannot be my own boss because I would allow myself to continue. Okay, let me continue a little bit, and Rami, please tell me when to stop. And also everyone is free to leave whenever one has to leave. So it's been almost an hour. So let me tell you the truth. What is definition of wavefront set? The definition is the following. So first, there is a short definition, which I even didn't write down. We consider the distribution character of the representation. It's a generalized function on the group. We consider it as the identity. It has a wavefront set. The collection of direction is actually cotangent directions in which this distribution is not smooth. It doesn't behave like a smooth function. But in characteristic 0, more is true. Near the identity, the character distribution asymptotically equals to a linear combination of Fourier transforms of Haar measures of nilpotent orbits. So if we take the character, we lift it using a logarithm, we restrict it to neighborhood of identity, use logarithm to lift it to the Lie algebra, and there it will be a combination of restrictions to neighborhood of 0 of Fourier transforms of measures of nilpotent orbits. So periodically it's equal, it's shown by Howe and Harishchandra. In the Archimedean case, it's asymptotically equal, near 0, the asymptotics near 0, due to Barbash-Logan. Then we take the wavefront set to be the collection of orbits with non-zero coefficients, and by wavefront O of pi, the union of maximal elements in this correction, maximal with respect to the closure order relation. That is, O is smaller than O prime if O lies in the closure of O prime. So that's the definition. But we use a theorem on equivalence. In the Archimedean case, it's equivalent to annihilator variety. And in the periodic case, it's equivalent to existence of degenerate Whittaker models. So let me say a couple of words on the periodic case. First of all, so the general, the theorem we prove is slightly weaker in the periodic case, but there is some evidence that the stronger theorem holds. First, why the evidence is just for GLN? Because for GLN, we have stronger tools. First of all, one has the Zelivinsky classification, and the wavefront set is easily described in terms of the Zelivinsky classification. And second, there are Bernstein-Zelivinsky derivatives that also talk very well to the Zelivinsky classification. And using this theory of derivatives, one can describe many models, especially those that have to do with some partial Whittaker models, like the Klitschko models. There, the corollary we obtain in the Archimedean case is proved for Klitschko models by Offen and Sayan. Then for Jacquet quotients, it's proven for representations of specific nice form, ladder representations, but this includes all unitary representations of Arthur type. So the corollary we have for Jacquet quotients is proof for ladder representations by Lapid and Mingus. And for restriction from GLN plus 1 to GLN, it's proved for representations of Arthur type by Maxim Gourevitch and K. Yuan Chan. Actually, what they proved, completed by K. Yuan Chan, is the complete non-tempered Gauss-Prasad conjectures for this case, for representations of Arthur type. So this, together with the Archimedean case, is evidence that the conjecture should hold in the periodic case as well. So what we actually prove? We actually work with Whittaker orbits. They're defined in the following way. For any nilpotent element of G star, we can identify it with an element of G, F, using the killing form. And then a nilpotent element of G, using Jacobson-Morozov theorem, can be completed to an SL2 triple, FHE, in G. And we form the following nilpotent algebra. We take all eigenspaces of H with eigenvalues 2 and higher. That's a nilpotent Lie algebra, because if we take Lie brackets, we get to eigenvalues 4, 8, and so on. 4, 6, and so on, sorry, in G. To this nilpotent Lie algebra, that corresponds a unipotent subgroup. It's exponential in G. And we consider the following. For any representation which I denote by big pi, because it doesn't have to be admissible, it can be huge, we consider the following quotient. We consider its co-invariance with respect to this nilpotent subgroup with a character given by phi. So just pairing with phi defines the character of this Lie algebra, which we exponentiate to a unitary character of this Lie group. And if the co-invariants don't vanish, we say that this phi belongs to the set WO of pi. So co-invariance vanishing means that there exists a V phi invariant function. It's equivalent by dualizing the space of co-invariance. And Mauglin and Valspurger actually proved that the closure of the set equals the closure of the wavefront set for irreducible representations. Now, our theorem is actually the following. Being H-distinguished is equivalent to being a quotient of the space of Schwarz functions on G mod H. So, and Mauglin and Valspurger translate wavefront set to Whittaker orbits. So the WO of Schwarz functions, we proved that it includes the nilpotent cone intersected with GH perp and is included in the closure of GH perp. Intersected with nilpotent cone because by definition we start with a nilpotent phi. So that's what we proved. But it translates due to Mauglin and Valspurger. Well, let me tell you how we proved it. We need some more ingredients. We need the Kazhdan action. Actually, this is the action that defines the Kazhdan filtration for W algebras. The action is the following. It's action of multiplicative group by we multiply an element T from the field by H. We exponentiate this. What does it mean, exponentiate? Well, H defines a torus, a Cartan, one-dimensional subalgebra of G, which also defines a one-dimensional torus in the group. So there is a map XPTH for small t. And this acts on psi by the coadjoint action, but we also multiply this by T squared. Why do we multiply by T squared? So that it fixes phi. So on the eigenvalue, on eigenspace -2, the exponentiation, this action acts by -2, then we, by T to the -2, then we multiply back by T squared, and this cancels out. So this action fixes phi. And it retracts the eigenvalues, eigenspaces higher than -2 to 0. And it keeps eigenspaces -2. Then it also explodes eigenvalues -3 and on. Then second, non-vanishing of co-invariants in Schwarz functions is equivalent to existence of invariant distributions. And for existence of invariant distributions, there is a necessary condition due to Bernstein. And for nilpotent groups, it's also sufficient. It's very easy. On the stabilizer of every point, the character should vanish. That's a necessary and sufficient condition for nilpotent groups and their algebraic characters. It's just it should vanish on the stabilizer. And what is stabilizer in the case of G mod H? Its Lie algebra is the intersection of the Lie algebra of the group acting with the twist of the Lie algebra of H, twist by the point. So G here represents a point, double cosine. So this should hold for for this not to vanish, this should the restriction of the character should be 0 for some point G in G. Then we get that on the orbit there exists a distribution, and then the distribution extends because the group is nilpotent. So these two ingredients are enough for us. So let me remind you the theorem that Whittaker orbits include GH perp and lie in GH perp closure. Here is the proof. So first, for the first inclusion, if you have phi in GH perp, so it's little g times H perp for some G, then it vanishes on the G of H. It's just equivalent to this condition. Also vanishes on the intersection. So there exists an invariant distribution, thus there exist co-invariants and Schwarz functions. And that's it. To the other direction, non-vanishing means that phi vanishes on G of H, but intersects it with the Lie algebra V phi. So phi lies in the orthogonal complement to the intersection, which is sum of orthogonal complements. Here we just write orthogonal complement to GH is the same as G applied to orthogonal complement of H. Here, the orthogonal complement to eigenvalues greater or equal to 2 is eigenvalues strictly greater than -2. It's this. G star H greater than -2. So direct sum of all eigenvalues, eigenspaces of little h with eigenvalues greater than -2. And then we apply the Kazhdan action. Kazhdan action preserves phi. It keeps big G times H perp inside it because the action consists of scaling, which keeps H perp, it's conical, and conjugation action, which keeps us inside big G applied to H perp. So this stays inside GH perp, this stays phi, and this shrinks the Kazhdan action. The exp of th multiplies this by t to power bigger than -2, and then we multiply by t squared, so it's multiplied by positive powers of t. If t tends to 0, this tends to 0, so this shrinks. And then we take limit, and we get that phi is in the limit of GH perp, namely in the closure of GH perp. So this is the proof. And that's the end of my talk. Thank you very much for your attention. Thank you for staying with me over time. Questions, please.
Okay, no questions?
So let me add that this works also for non-homogeneous spaces. So instead of G mod H, we could have X, and instead of GH perp, we would have the image of the moment map.
Mm.
Exactly what this is for G mod H, it's the image of the moment map.
So it's direct corollary from the transitive space case, or it's analogous?
It follows, yes.
You just analyze it orbit by orbit, or if you distinguish with respect to one of them? So
actually, for this p-adic theorem, we prove it directly for X, and for the Archimedean theorem, we deduce it.
But it just follows from the fact that if something is distinguished with respect to a non-transitive space and it distinguished with respect to one of its orbits?
So in the Archimedean, in the non-Archimedean case, yes. In the Archimedean case,
just not two, yes?
It's just not true. You have those transversal derivatives.
Yes.
But,
But they don't change too much. Yes.
But they don't change anything, because in the Archimedean theorem, you're actually allowed to use not the trivial representation of H, but rather any finite dimensional representation of H. So you take symmetric powers of normal bundle to compensate for this.
And do you always have finitely many orbits or in those cases?
Yes, yes. So non-homogeneous, okay, sorry, let me correct myself. In the p-adic case, no, we can put here any x. We didn't need it to be spherical. We also don't need it to have finitely many orbits. It just works. So actually also this statement, as formulated here, also works in the Archimedean case. What is not known in the p-adic case is a theorem of Montgomery-Waltz-Purget that would translate this to wavefront set. But in the paper with Eitan, we just prove this in both cases uniformly. Now for the Archimedean theorem, we assume that H is spherical. So instead we can, G mod H, consider X, which is a spherical space. But being spherical implies that it has finitely many orbits under the group. So one thing we hope to do in the future is to translate the Archimedean proof to the p-adic case, but one needs some new tool. You cannot just use the algebra. And also the question is, in the proof, there is certain algebraic closure. The question is, maybe in the statement there should be some algebraic closure. But on the other hand, here is some other statement without algebraic closure. So maybe one does not need algebraic closure in the statement. And also one can formulate those conjectures slightly differently. We have formulation of a different formulation, non-equivalent formulation in the conjecture. In the preprints, I just don't know what is true. One deep conjecture is that this theorem of Montgomery-Waltz-Purget also holds in the Archimedean case. And another one is that this theorem by Rossmann also holds, not this, but the previous, the translation from one to another also holds in the Archimedean case. But I mean, I don't remember if I showed it, but yes, this theorem by Rossmann also holds in the p-adic case. Namely, in other words, that in the p-adic case, the wavefront 0 also lies in one stable orbit. And if you take a stronger formulation of our conjecture that appears in the preprints, it will imply this conjecture as well. But just conjecture so far. Again, proven for GLN. So for GLN or p-adics, everything you want is proven. But what about other groups? Further questions?
So, okay. So, sorry, I ask like so on this Lee-Wen-Wei's theorem, like, is there a criterion for like between H and O such that this is equal, like the inequality is equal? Like
here.
Yes.
So of course intersection can be empty, but if it's non-empty, it might well be the case that it always equals. It's the case for symmetric pairs. It's the case for H being a nil radical of the Borel, which is on the other extreme, a very non-reductive H. maybe it equals in general, I don't know. It's a question of reduceness. So if you take, so on the level of tangent spaces, it is. So this is a Lagrangian in the sense that if you take the tangent space to this intersection, it's a Lagrangian subvariety in O.
Yep.
But the question is that maybe the tangent space is bigger than the intersection because the intersection is non-reduced.
Okay, thanks.
No case is known when it's actually non-reduced. All right, so thank you all for coming. Next week, Vitek Gunn will speak on theta correspondence. And in 2 weeks, Solomon Friedberg will speak on some generalization of theta correspondence. At this point, I stop sharing. And stop. Stop recording.